Hi guys, and welcome to Algebra 2, 10.4. We're working on today probabilities of compound events. And so part of this is going to be a little bit of review from 10.1 to 10.3, but then most of it's going to be new and working with some Venn diagrams. So we're looking at ways to organize information, which we had already talked about before. We have several ways that we can organize information. One way it was that we just made a list of all of the answers. Another that we did with the dice was that we graphed the sample space. Another is we looked at a table, like a two-way table, a lot of times to organize the event data. We used a Venn diagram. We also used a tree diagram. That was the one with the branches that were going off. And then each event was a new set of branches. So those are the main ways that we've organized information so far. Again, today we're mainly working with Venn diagrams. So here you go. Two events. If we consider both of them happening at once or not at all, if they may intersect or they may not. If they do, they're called a compound event because more than one thing is happening at the same time. So these Venn diagrams represent, the shaded part represents the part that we're looking at. So union would mean anything in A or anything in B or the part that's in the middle. You don't count the part that's in the middle twice just because it happens to be in A and B. But anything that's in any of those would be the union, right? It's anything A has, anything B has, and anything that they would happen to have in common. So the symbol for that would be A union B, and it's or. You can also read it as A or B. And we talked about this before break, but it's been a long time. Here in the Venn diagram, we have A and B labeled. Also the U here in the corner means the universal set, and that's just the set of all the outcomes. So that's not a union symbol there. That actually just is U for the set of all possible outcomes. All right. So then for the next one, if we're looking at the intersection of A and B, it's only the part that they would have in common. And so it's only the shaded part in the middle. We use the intersection symbol. Remember in class I talked about the union symbol looks like the letter U, the intersection kind of looks like the letter N, or you could put a base on it and wheels and make it a car and then think about it as an intersection that way. But that would be called A and B, and that means the intersection. And then one new vocabulary word for you here. Two events are called disjoint if they don't have an intersection. So it's possible that they could, but they end up not. For instance, if I sample fourth period and I say, raise your hand if you like to swim, and 5 people raise their hand, and then I say, raise your hand if you don't like pizza, and another 6 people raise their hand. If the 6 people and the 5 people are two different sets of people, then it was possible that they could have overlapped, but they didn't. And so because there's no overlap, they have nothing in common, right? They have no intersection. And so this is what it's saying down here, is that A intersect B, down here at the bottom, A intersect B, and then this is not called no solution. It is the no solution symbol, but that also can mean undefined. And then in this case, it means the null set, which means the empty set, which means no solution. Like it means they don't intersect at all. So it's a pretty minute difference in what you call them. Really, they have the same idea as far as the concept of their meaning, but it's technically not no solution. Okay, so what I would like you to do is pause the video and draw this Venn diagram, and then see if you can fill in the Venn diagram with the appropriate numbers. We did something like this before break. And so just as a refresher, I'm not going to wait on you to do that, but I will, like I said, pause, and then we'll start in 3, 2, 1, Okay, let's check your numbers. Hopefully you paused it and you tried to get this done. So 40 students make up the entire sample space. So all the numbers when I'm done have to add up to 40. We're going to find the most specific number. So either that's a number that would be hanging on the outside or the number that would be the intersection. One of those numbers, if we have either one of those, would be easier to start with. So in this case, this would be 2 said that they didn't like either. So 2 is going to be floating around here in the universal space. And then 34 and 25 obviously add up to more than 40. So 34 have to be in the pizza circle. That would be both sections added of the pizza circle would have to add to 34. And both sections of the swimming circle have to add up to 25. But the overlap is currently being counted twice in the 34 plus 25. So we can figure out how much the overlap is by adding up 34 plus 25, which you're welcome to do in your head, but I'm going to show my work down here. 34 plus 25, which is 59. And then we know that the total union would need to add up to 38 because that's the 40 minus 2. So we know that I only have 38 left. And so what's the difference here between the 59 and the 38? Because that'll tell us what that overlap is. So if I subtract the 59 that I got from adding up the two numbers, and I subtract the 38 from that, I get 21. And so 21 must be the size of the overlap because 59 is 21 too high. So that must be that part in the middle that had been counted twice. And then from there, we can figure out what would have to just go in the pizza and just go in the swimming. If 34 like pizza, then I know that there would have to be 13 more who like pizza but don't like to swim. That way the 13 and the 21 would add up to 34. And if 25 like to swim, then I know that there's a 4 that goes in there. So there would be 4 people who like to swim who don't like pizza. And then you can check yourself by adding up all those numbers and making sure that those numbers add up to 40, which they do. And then the question says, how many like pizza and swimming? And so the word and means they have to like them both, which means I'm going to look at the intersection, which would be right here. And so the answer for that would be 21. Hopefully you either got that right ahead of time or it makes sense to you. Here is the formula that goes along with that. So I know that this looks a little bit overwhelming. It's a lot of writing, but it's not actually that terrible. This is just the formula that goes along with what we just did. And it says, for any two events, the probability of A or B, which is that union, would be the probability of A. So I'm going to draw this for you with the Venn diagram. The probability of A, so whatever that is, and also the probability of B, so whatever that is. But then notice that in my shading, I've counted that intersection point, or the intersection area twice. So we're going to subtract out one of them, right? We're going to subtract out the overlap. And that'll give us the probability of that union. Now, just a little point of notice. The formula is given with probabilities. The Venn diagram that I did on the last page was not with probabilities. It was with the number of elements in the set. So all of the formulas that we're doing are true regardless of whether we're looking at the number or whether we're looking at the probability. But they are two different things. Okay. Then if we go down to this second one, if A and B are disjoint, let's think about what that means. Disjoint means that they don't intersect at all. Then the probability of A or B, if we look at the top formula, would be the probability of A and the probability of B. But if they're disjoint, then the probability of their intersection is just 0 because they're not going to intersect if they're disjoint. So you can just get rid of that part and you can say the probability of the union would be just the two individual probabilities added up. This is refresher. This means not A, right? Or A complement. So here's your example. I've given you two events and I gave you the probability of their union. And so we want to figure out, are they disjoint? Are they overlapping? What's going on here? So the easiest way I think to do this is to draw the Venn diagram, even if it doesn't ask you to draw the Venn diagram. You can do it completely algebraically just by working with the numbers and the formulas as well. But that to me is a little bit more thinking because you're trying to figure out all the formulas and wrap your head around that instead of just drawing a picture. So in this one, the probability of A is 0.5 and the probability of B is 0.3. If I add those up, I get 0.8. But the probability of the union is 0.7. So they can't be disjoint because the probabilities added up don't equal the probability of the union. In fact, I can say, okay, so if I add them up and I get 0.8, but the union has to be 0.7, then what was the overlap? In that case, the overlap was 0.1. And then once I find that the overlap, that's a decimal point, by the way. Once I find that the overlap is 0.1, then I can say, okay, so that means what's left for the other part of the A circle would be 0.4, and what's left for the other part of the B circle would be 0.2. And then if you look, the A circle in total adds up to 0.5, right? Here's the A circle in total that has the 0.5, and the B circle in total has the 0.3, but the probability of their union, if I add up those three, would be 0.7. So are the events overlapping? Yes. What would be the probability of the intersection? 0.1, because I already found that, right? There's no additional work. And then what's the probability of not B? I don't actually need to go to my picture for that. I would just find the probability of B. If the probability is 0.3, then the probability of not B would be 0.7. Also, if I wanted to fill out the rest of the Venn diagram, what would be left floating in the universal space? Do you know? Figure it out. It would be 0.3. Because 0.7 is what I get for the union, which means that whatever's left, right, the whole rectangle, the whole universal space always has to add up to 1. Okay. Here's another one. This one's a little bit trickier because it tells us for the third piece of information that A and B are independent events. And so we have to use that, which we did before break, to find some other things happening here. So if A and B are independent events, we have a formula for the probability of their intersection, right? Independent events mean they don't depend on each other, like flipping a coin twice, right? The outcome of the first time does not affect the outcome of the second time. So if the events are independent, the probability of both events happening, which would be A and B, is equal to the probability of A times the probability of B. That should be in your notes from before, but you might want to put it in your notes again. So I'm going to use that to find the probability of the intersection, and then from there, the rest of the problem will just be filling out the Venn diagram like we did before. So in this case, 0.5 times 0.3 would be 0.15. And so I can say, okay, that means this middle part here of the intersection would be 0.15. And then, right, so that's what I use the definition of independent probability for. There you go. Then, once I've done that, I can go ahead and fill out the rest of the A circle and the rest of the B circle and finish the problem. So the rest of the A circle must be 0.35 so that they add up to 0.5. The rest of the B circle must be 0.15 so that those add up to 0.3. And if I add all those up, 0.35, 0.15, and 0.15, I get 0.65, which means that the universal space floating around must be a 0.35 as well. So now that I have that filled out, these questions should be nice and easy. Are the events disjoint? Nope. Are they overlapping? Yep. And then what's the probability of the union? That would be 0.65. The union, remember, is adding up anything that's in A or B or both, but you don't count the both twice. Here's one that was one like we did before break. What's the probability that the sum of the numbers rolled is a multiple of 4 or is 5? So when we did this before break, we did this by graphing the sample space. We said we could have 1, 2, 3, 4, 5, 6 on the first roll, and 1, 2, 3, 4, 5, 6 on the second roll. Go ahead and make your dots, or you can write out the sums if you want, and then see if you can figure out this answer. Pause the video until you do that. And then in 3, 2, 1, here we go, finding the answers. So a multiple of 4 for the sum of the numbers. So the sum of the numbers could be 4, which would be 3 and 1, 2 and 2, or 1 and 3. Or the sum of the numbers could be 8, right? Because that's also a multiple of 4. So that's so for them to add up to 8 would be 6 and 2, 5 and 3, 4 and 4, 3 and 5, 2 and 6. Or if the 12 is also a multiple of 4, so 6 and 6. There you go. All of those would be multiples of 4. Then it says, or what's the probability that it's that, or that it's 5, that the sum of the numbers is 5. So the sum of the numbers being 5 would be 4 and 1, 3 and 2, 2 and 3, and 1 and 4. These are examples of disjoint or mutually exclusive events, because the sum cannot be both a multiple of 4 and 5, because 5 is not a multiple of 4. So we're just going to count these up. We know that there are 36 possible choices. Because they are mutually exclusive, it just means I can just add the red ones that I have circled with the purple ones that I can have circled, and I don't have to subtract out any overlap because there is no overlap. So when I add those up, I get 13 out of 36, it looks like. Okay. Here we go. 2 left. Try this one on your own. Go ahead and pause the video and try this one on your own, and then we'll do it together. And I will also pause the video, and we'll do this together in just a sec. Okay, so here we go. Hopefully you had a chance to try this problem. I actually went and got a sheet to cover up the window in my door so that you can see my face. I know that it's awfully bright outside. The joys of working from home. So here we go. There's 113 that are either varsity athletes or on the honor roll, which means 113 would be the union there. So 74 that are varsity athletes and 51 who are seniors, if I add those up, they add up to 125. But there's only 113 that are in the union, so I need to see what the overlap is by subtracting. Hopefully that's what you did as well. And you get that there are 12 in the overlap. Once I know that there are 12 in the overlap, then I can go ahead and figure out the remaining pieces, right? If I wanted to. In this case, I don't need to figure out the entire Venn diagram, because if we look at the question says, what's the probability that a randomly selected senior, so that's out of the 200 seniors, right, not just the ones that are athletes or on the honor roll, what's the probability that any randomly selected senior would be both? Well, both was the 12 that I just came up with. So the probability that that senior is an athlete and on the honor roll would be 12 out of 200, which we know reduces to 6 out of 100, which would be 0.06. And then, ta-da, you're done. And last, so here's our last example. I know that it's a lot of reading, so let's read it together. The American Diabetes Association estimates that 8.3% of people in the United States have diabetes. Suppose a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for those who have the disease and 95% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. What's the probability that that's correct? So in this case, we could organize this with a Venn diagram. We also could organize this with a tree diagram. And so I'm going to do this one with a tree diagram just so you can see. And then if you did it with a Venn diagram, then you can check and compare, and we should have the same answer. So first off, you either have diabetes or you don't, right? So I'm going to let the D be diabetes, and then D complement would mean you don't have diabetes. Then the second branch would be with the test, right? So is the test accurate or is the test not accurate? And if you don't have diabetes, is the test accurate or is the test not accurate? So those are our events, and then we'll put the probabilities on the branches. So if 8.3% have diabetes, then that means the 91.7% don't have diabetes. So that tree is filled out. Then it says that the test is 98% accurate if you have the disease. So what would that mean? That means that you take the test and then it tells you that you have diabetes and you actually do have diabetes. That means that for 2% of the people, they do have diabetes, but the test is not accurate, which means that the test would tell them that they don't. Then it says it's only 95% accurate for people that don't have diabetes, which accurate in this case would mean that you don't have diabetes and it tells you that you don't have diabetes. That means for 5% of those people, they don't have diabetes, but the test is not accurate, which means the test would tell them that they do have diabetes even though they actually don't. The lab gives the test to a randomly selected person. What's the probability that the diagnosis is correct? So correct would mean I want this trail that they have diabetes and it's correct, or this trail that they don't have diabetes and it's correct. And so for each one of those trails, we're going to have to multiply those numbers. I'm going to grab the calculator. If we do 0.083 times 0.98, then we get 0.08134 for having diabetes and correctly diagnosing that. And then if we multiply 0.917 by 0.95, we get 0.87115. And so that would be this one, which would be not having diabetes and correctly diagnosing that as well. And so the diagnosis being correct could be either one of those things, right? And so I'm just going to add those up to see what my end result is. And I get 0.95249. So the probability that it's correct, which would be either one of those cases, would be 0.95249. All right, thank you for hanging in there with me. I know this was a little bit of a long lesson. I tried to do a lot of examples, so hopefully you hung in there and you took some notes, and now you're ready to do your 10.4 homework. Have a lovely rest of your day.